This is SK Ghosh. I would like to welcome all of you to our to the continuation of our training and capacity building program, which is part of component S9 of Rajuk's Urban Resilience project. I suppose most of you have been attending these seminars, so I do not have a lot to tell you. Today, we will talk about the wind load provisions of Bnbc 2020. This is module S4, structural 4. This is the second time we are getting together after Eid, and now it will be every week until the middle of July. Today, I have probably 4 hours worth of material. I was aware as I was putting the material together that it will not be possible to go over everything in the 2 hours and a quarter that we have. So I first of all, I did want to put together and give you a comprehensive slide set, which I think you will find to be useful reference material for quite a while to come. And I do want to go over the basics, the fundamentals of the wind design, because I believe it is extremely important to understand why the code tells us to do what it tells us to do. That understanding, I think, is basic. So I will go through the background material, however long it takes, and then depending upon the time left, I will cover the remaining material kind of selectively. I definitely do have some plans in my mind, but those are kind of flexible plans. So just so that you know. So in the beginning, it is background, and some of it you may consider to be elementary. Please bear with me if you think that it is too basic. I think you will relate to it as we go. So the very first thing, wind loading, is the effect of the atmosphere passing by a stationary structure attached to the Earth's surface. As I said yesterday, every structure we put up stands in the way of wind. And because free wind flow is being obstructed by the structure, the wind will do things to the structure. It will apply pressure on some surfaces. It will apply what is called suction negative pressure on other surfaces, and we as engineers have to deal with those. Wind loads are controlled by atmospheric, having to do with the atmosphere, obviously, and aerodynamic effects. Aerodynamics have to do with the structure, the shape of the structure. Has nothing to do with the atmosphere. So there are atmospheric effects that control wind. There are aerodynamic effects that control wind. The basic equation that we use in wind design is the last line on the slide. P, the pressure due to wind, is equal to Q, which we call the velocity pressure, multiplied by a gust effect factor, multiplied by an external pressure coefficient C sub P. Obviously, each of these terms will be explained in quite a bit of detail in the rest of the seminar. But for now, P, the pressure due to wind, is equal to velocity pressure Q multiplied by the gust effect factor G multiplied by the external pressure coefficient C sub P. Out of the three terms, Q is determined entirely by atmospheric effects. It has nothing to do with the structure. The C sub P is, on the other hand, entirely a function of the aerodynamics of the structure, has nothing to do with the atmosphere. G is a combination of both. It is a function of atmospheric effects as well as the aerodynamic effects. When we say atmospheric effects, it kind of has two parts. Meteorological effects having to do with the flow of wind, and boundary layer effects. I will explain that in just a little bit. So meteorology provides a description and explanation of the basic features of atmospheric flows. A discipline within that, climatology, has to do with the prediction of storm conditions at a given geographic location. So climatology has to do with the prediction of storm conditions. When we use the word storm, climatological effect, these are the various types that we typically deal with. Thunderstorms that you are, I'm sure, all familiar with. Tornadoes, in depending upon where you are, tornadoes don't strike everywhere. Cyclones. Cyclones are called hurricanes in this part of the world, the other side of the Atlantic. And the word typhoon is used in some parts of the world. They are very similar storms. Special regional effects that can be caused by wind blowing through mountain gorges, things like that. Those are things we also have to contend with if we are going to design successfully against wind. So thunderstorms, tornadoes, cyclones, and special regional effects. Thunderstorms, the word thunderstorms, it is applied to a variety of associated wind phenomena. Predicted thunderstorm activity controls, this may or may not be of interest to you, but predicted thunderstorm activity controls vast majority of US wind loads. And I am 95% sure that is true also in Bangladesh. It's the thunderstorms that typically determine the wind in most parts of the country. And because of that, most of the inland United States has very similar design wind speed. So until you go to what is called hurricane-prone regions, the wind speeds do not vary much because they are all determined by thunderstorms. Yeah. The design wind speeds that we have in ASCE 7, or the ones that are included in Bnbc 2020, do not include the effects of tornadoes. That is because tornadoes are very localized in time as well as space. Okay, they move on quickly, so they are localized in time, and they hit relatively small areas, and then they move on. So localized in place. So probability of occurrence at a particular location, because they are so localized in time and space, the probability of the occurrence of a tornado at a particular location is so low that tornadoes simply do not appear in the 50-year statistical storm data used to formulate the inland portion of the map. So the 50-year refers to the fact that in Bnbc design, we design standard occupancy structures like office buildings, apartment buildings for 50-year return period wind. Wind event that is expected to happen once in 50 years. Tornadoes are so short-lived that in that it simply does not feature in that 50-year return period wind speed. It's too short-lived and too localized. Okay. Bnbc in section 2.4.2 actually tells you tornadoes have not been considered in developing the basic wind speed distributions. That is the language in Bnbc itself. By the way, I probably should have mentioned to start with that the wind provisions are in section 2.4 of Bnbc 2020, which is part of part 6, chapter 2 of the code. This is what a typical tornado looks like. If you haven't seen one or seen the picture of one, as you see, it is localized in space. It doesn't cover a lot of area. And these things typically move on very quickly. Let's go to cyclones, which are, as I said, called hurricanes in this part of the world. As the picture shows, hurricanes or cyclones do not happen everywhere. There are parts of the world where they are quite common, and then there are other parts of the world where it simply does not happen. South America, for instance, have significant coastlines on the Atlantic and the Pacific, but cyclones or hurricanes are unknown in South America. North America, on the other hand, the United States, it's unbelievable how many big storms hit every season. Okay? So Bangladesh is one of those unfortunate countries that does experience cyclones from time to time, and that is something that obviously we have to be concerned about. There is also a hurricane season on this side of the Atlantic, west side of the Atlantic, going to the Pacific. The hurricane season, as you see, is basically from August until October, November. It is not that hurricanes don't happen outside of that, but that's very rare. The hurricane season or the cyclone season in Bangladesh, which is obviously way on the other side of the Atlantic, it's Indian Ocean and beyond. The season is reversed. In the Indian Ocean, north of the equator, where Bangladesh is, tropical cyclones can form throughout the year on either side of India. Although most frequently, this is the important part, between April and June. So this is before the beginning of the hurricane season here, and between October and December, this is pretty much after the end of the hurricane season here in the US. So between April and June and between October and December. On the east side of the Bay of Bengal and on the east side of India is obviously the Bay of Bengal. That the cyclones in the Bay of Bengal are the ones that concern us. On the west side of India is the Arabian Sea, and that is also subject to cyclones, which obviously do not affect Bangladesh. A cyclone or a hurricane, unlike a tornado, covers a large area, as I think you can see from this picture. This is the state of Florida. This is southern United States. This probably is somewhere like Louisiana. Anyway, this is a huge hurricane sitting there, and this thing sometimes move very, very slowly, 3-4 miles an hour. Sometimes, other times it will move quicker. And the fact that such a big storm basically sits there causes a lot of problems. It is wind, it is rain, anyway. So cyclones that hit Bangladesh, one of the more recent significant ones, Cyclone Fani, 4th of May 2019 was the date. It originated in Orissa in India, then moved to the north and east. So this was kind of the path in Kolkata. It caused quite a bit of problem and destruction. By the time it got to Bangladesh, it had lost much of its punch. So there was a lot of foreboding, but not a lot happened. Luckily, in that last cyclone. Now, in this is something I wanted to bring up. This is from the terms of reference of our other project S9, not other project, of our project S9, which has to do with code enforcement. This is a World Bank document. In recent years, Bangladesh has reformed its approach to cyclone and flood risk management and preparedness, triggered by major loss of life and assets, notably during the cyclones of 1970 and 1991. Those are the two big ones in recent memory. Government of Bangladesh, civil society, and international development partners have demonstrated that investment in the systems and structures of flood risk management and cyclone preparedness saves lives, reduces economic loss, and protects development gains. As such, Bangladesh is cited often in the rationale for investment in disaster risk mitigation activities globally. So Bangladesh has been successful in containing the effects of cyclones. And then the World Bank document goes on to say that earthquakes are a different story, and that much of S9 is devoted to what do we do about earthquakes. But it is good to know that Bangladesh has been successful, very successful, in containing the effects of cyclones, which are relatively not uncommon in the country. So size and duration of cyclones makes much higher probability of striking a given coastal location, unlike tornadoes, which are unlikely at a particular location. Cyclones control design wind speeds in cyclone-prone regions, and those are defined in Section 2.1.3 of Bangladesh National Building Code as areas vulnerable to cyclones. In Bangladesh, these areas include, this is official definition of cyclone-prone regions. In Bangladesh, these areas include the Sundarbans, southern parts of Borishal, Patuakhali, Patia, Vola, eastern parts of Chittagong, and Cox's Bazar. The eastern part of Chittagong mystifies me. The eastern part of Chittagong borders on India and Burma. It's totally landlocked. Is the western part of Chittagong that is on the Bay of Bengal. So I kind of wondered about the eastern part. Anyway, so I believe they mean western. Why it is said eastern, I don't know. Anyhow, so this is the definition of cyclone-prone region. The Sundarbans, southern parts of Borishal, Patuakhali, Hatia, Bola, eastern parts of Chittagong, and Cox's Bazar. This is the wind speed map of Bangladesh that is part of Bnbc 2020. I will not talk about the map values now, that is yet to come, but I did want to show you the hurricane-prone regions, which are red on the map. So this is southern Bengal, and then you come here, western parts of Chittagong and Cox's Bazar. Okay. So hurricane-prone regions or cyclone-prone regions in red on this map. The basic wind speed map, as it is called, that is part of Bnbc 2020. Yeah. Now this tells you that away from there, the southern coast, if you are in Dhaka, well inland, the cyclones are not your problem. They do not determine your design wind speed. On that map, the wind speeds are in meters per second, which I have no idea of. You tell me 80 meters per second doesn't mean anything to me. So the range of wind speeds on that map is from a low of 41.4 meters per second to a high of 80 meters per second in the cyclone prone regions. 80 meters per second is 288 kilometers per hour, which is 179 miles per hour. That's a number I understand. And 41.4 meters per second is 149 kilometers per hour, which is 93 miles per hour. Yeah. So those numbers tell me that, well, for comparison, in the in well, how should I? This is pretty much the same range of wind speeds here in the United States. If we go back to older standards, which the 93 miles per hour, we had wind speeds as low as 85, and the 179 miles per hour south of Miami in the Florida Keys, we go up to 200, maybe 210 miles per hour, something like that. So this is a comparable range. The special wind regions. This is section 2441 of Bnbc. The basic wind speed shall be increased where records or experience indicate that the wind speeds are higher than those reflected in the figure that I showed you. Mountainous terrain, gorges, and special regions shall be examined for unusual wind conditions. Most of Bangladesh doesn't have that until you go to Chittagong hill tracts, and then these are factors. The authority having jurisdiction shall, if necessary, adjust the values given in the figure to account for higher local wind speeds. The authority having jurisdiction. So that would be Chittagong Development Authority, for instance. Such adjustment shall be based on adequate meteorological information and other necessary data. Okay, so coming back to P is equal to QG C sub P. Remember the velocity pressure, the gust effect factor, and the external pressure coefficient. I will take you through each of those terms in detail. So we absolutely need to know those terms, and we need to know them intimately. Okay, so the velocity pressure Q you will seldom see without a subscript. It is always Q sub Z or Q sub H. Q sub Z is the value of Q at a height Z above ground level. So here it will be Z feet. In Bangladesh, it will be Z meters or whatever. Okay, so Q sub Z is at any height Z above ground level, and Q sub H would be the velocity pressure at the mean roof height level of the structure. Mean roof height is something I will define just a little bit later on. Okay, so Q sub Z, Q sub H. Q sub Z is a constant 000613 V squared, that is the wind velocity squared, and that velocity has to be defined, and there is quite a bit of complexity to it. Then three coefficients, K sub Z, K sub ZT, K sub D, and an importance factor I. So there are five variables in this equation: V, K sub Z, K sub ZT, K sub D, and I. Now in this equation, Q sub Z is in kilonewton per square meter, and V is in meters per second. Very important. This is why the map gives you velocity in meters per second. Okay. So in ASCE 7, this equation is written without the three zeros, but then Q sub Z is in Newton per square meter, whichever way you like it. So the constant, first of all, is 1/2 of the density of air. So So what we have within parentheses is 1/2 rho v squared. And the significance of that term, I will explain a little bit later on. So for now, 0.00613 is 1/2 of the density of the air in the proper unit. And these units in metric, I have problems with, but it can be figured out. Okay. Uh, the V, basic wind speed. So from here on, it gets pretty serious. Okay, so the V is 3-second gust speed, first of all. It is 10 meters above ground. It is 10 meters above ground in exposure B and associated with a return period of 50 years. So there are 4 elements to V. It is 3-second gust speed. It is at 10 meters above ground. It is at 10 meters above ground of exposure B. And it corresponds to a 50-year return period. Okay. 3-second gust speed, what does it mean? Wind velocity changes from one instant to the next. It is never the same for any significant amount of time. So in design, we have no choice but to use some kind of an average wind speed. And 3-second gust speed is wind speed averaged over 3 seconds. Now, you do not take just one 3-second period and average wind speed over it. That won't be 3-second gust speed. Meteorological organizations, here it is NOAA, Bangladesh, I don't know what the agency is called. They will take an average over 3 seconds, then the next 3 seconds, then the next 3 seconds. And the highest value of these 3-second averages over a period of 1 year will be the 3-second gust speed. Okay. Then the wind speed changes with height above ground level. At the level of the ground, wind velocity is 0. As you go up, the velocity goes up. How quickly it goes up or how slowly it goes up depends on the roughness of the terrain, how rough the ground is. Okay, so it is important to specify where you are measuring this velocity, and it is measured at 10 meters above ground. What is the roughness of the ground? That's where this exposure B comes in. Okay, the exposure B is flat open country for now. Wind velocities are typically measured at airports, which is typically flat open country, and that's where that comes from. And then 50-year return period means this is a velocity that is expected to occur once in 50 years in very simple terms. Now the exposure B, I crossed out C and underlined B. In ACE7 at one time, there were 4 exposure categories, A, B, C, and D. Then A was deleted. We now have, for a long time, B, C, and D. Bangladesh National Building Code has taken B, C, D exposure categories of ACE7 and have renamed them A, B, and C. That has caused at least me a lot of headache in preparing these slides. But that's not the point. The point is that it makes it very difficult for you to go to AC7 for reference. You have to constantly remind itself that when you see exposure B in AC7, it means exposure A of Bnbc 2020. When you see exposure D in AC7, it is actually exposure C in Bnbc 2020. You always have to mentally do this translation, which is an unnecessary complication. So I kind of wish it were not done, but it has been done. Okay, so 00613 V squared, the V up to V part I have explained to you. The K sub Z is a combined height and exposure coefficient. It has a name that will come up, but that's unimportant. The V, as I explained, is at 10 meters above ground of exposure B. If that's all we know, we are not going to go very far with our wind design. What if we need to know the wind velocity at 20 meters above ground of exposure C? K sub Z will take us there. K sub Z will take us from V, which is at 10 meters above ground of exposure B, to wind velocity at any height above ground of any exposure. Okay. So K sub Z. Now, K sub Z, this is where the atmospheric boundary layer comes in. Atmospheric boundary layer is the layer of turbulent air in contact with the Earth's surface. It is the first kilometer or so of the atmosphere. All buildings exist in the atmospheric boundary layer. You have to understand that there is no building that is more than 1 kilometer tall. The tallest buildings we have built are in the 1,000 feet range. That would be 300. That's a third of a kilometer. Above this layer, the atmospheric boundary layer, wind speed is substantially constant with height. So in this figure, we have so as I mentioned, at one time we had 4 exposure categories in AC7, A, B, C, and D. A was middle of large cities, B, suburban exposure, C, flat open country, D, wind blowing over a large body of water. A was dropped at one point, B, C, and D remained, and B has been renamed A in Bnbc, C is B, D is C. Okay, that much I told you already. Now, this slide tells you that the smoother the ground, the quicker the wind velocity picks up with height. So if exposure is C, wind velocity picks up very quickly. If exposure is B, then wind velocity increases with height much more slowly, as shown in the picture. And these heights that are given are the thickness of the boundary layer. Okay, it is also called gradient height. So for exposure C, I did not or forgot to change this. So for exposure C, the thickness of the boundary layer is 700 feet, which is 213 meters. For exposure B, it is 900 feet, which is 274 meters. And for exposure A, it is 1200 feet, which is 357 meters. Okay. So you see the combined effect of height and exposure. It tells you how quickly wind velocity increases with height above ground level. The relationship, so what is plotted on the previous figure, it is mathematically can be expressed like this. K sub Z is a constant times Z, any height above ground level, divided by the gradient height that I talked about, the 700 feet for what we call exposure D, to the power 2 over alpha. The alpha value is given in AC 7 and Bnbc. Alpha is the power law exponent. It is 7, 9.5, and 11.5 for exposure A, B, and C respectively. So if you know your exposure, you will be able to calculate K sub Z at any height above ground level because Z sub G is given in Bnbc and alpha is also given in Bnbc. So that's K sub Z. K sub Z is also given in tables, actually, and that's typically what we use. If we go beyond the tabulated values, the tables go up to 500 feet. Beyond that, we use the equation. K sub ZT is a topographic effect factor, as we call it. So if your structure is located on the upper half of a hill, a ridge, or escarpment, those terms are defined in Bnbc. It will have to contend with higher wind pressures than if it were located on level ground. Okay, that's what this picture tells you. And the K sub ZT coefficient accounts for that fact that a building sited on the upper half of a hill, ridge, or escarpment has to contend with higher wind pressures than a structure located on level ground. Okay. K sub D is called a directionality factor. So at pretty much at every location, you have a predominant wind direction. This I forget now, was something like Houston. I don't remember. Anyway, wherever it was, the northwest wind is the predominant wind. Southwest comes next. The other directions, you have lower wind. So southwest wind will cause the most effect on our building. The point is that just like wind velocity, wind direction also changes from one instant to the next. It is never the same for any significant length of time. So wind can blow along the most critical direction of a building, let us say in this location, the northwest direction, only instantaneously. The very next instant, the wind direction will have changed and it will no longer be along the most critical direction. The directionality factor K sub D takes this fact into account. And for all buildings, K sub D is 0.85. So we are decreasing the highest wind speed 15% to account for the fact that wind can blow along the most critical direction only instantaneously. Okay. So that's K sub D. Now, the return period, which will lead us to the importance factor I. That's the last element that I have not explained to you yet. So return period, also known as mean recurrence interval, used for the statistical determination of the predicted wind speed. Mean recurrence interval of 50 years is used for normal use structures. This is true of ASCE 7, this is true of Bnbc. 50-year return period for standard occupancy structures, normal use structures. For critical facilities, hospitals, police stations, fire stations, we use 100-year return period wind, rarer wind events. And for structures where no life safety is at stake, like a barn in a farm, we are allowed to use 25-year return period wind, more frequent wind events than the 50-year return period wind. The use of the 100-year return period wind for hospitals and so forth is mandatory, but the use of 25-year return period wind for unimportant structures is permitted, not mandatory. You are allowed to do it, you don't have to do it. So since we are using 3 return periods in design of structures of different occupancy and use, do we need 3 different maps in the standard? And the answer is no. ASCE 7 committee determined quite some time ago that the ratio between 50-year return period wind and 100-year return period wind is substantially constant. And so that we can convert to 100-year return period wind from 50-year return period wind using a multiplier, and that multiplier is called an importance factor. So if we take 50-year return period wind, multiply that by an importance factor of 1.15, we get, to a reasonable degree of accuracy, 100-year return period wind speed for design purposes. Similarly, to go down from 50-year return period wind to 25-year return period wind, we use an importance factor smaller than 1. Happens to be 0.87 in inland areas and 0.77 in cyclone-prone regions. Okay, so we have one wind speed map corresponding to a 50-year return period. When we need to use 100-year return period wind, we apply an importance factor of 1.15. When we need to go down to 25-year return period wind, we apply an importance factor of 0.87 or 0.77 as the case may be. Okay, that brings me now, so all the parts of Q have been explained. So we now come to G, the gust effect factor. Gust is rapid fluctuation of wind. Ordinary structures are sensitive to peak gust of about 1 second duration. 1 second. Before we started using 3-second gust speed as the basis of design, that started back in 1995. We used to use as the basis of design what was called fastest mile wind speed. Okay? So modern wind design started back in 1972. From 1972 through the mid-90s, we used fastest mile wind speed as the basis of design. When we say 3-second gust speed, the averaging time is 3 seconds. When we say fastest mile wind speed, the averaging time is the time it takes for a mile of wind to go through the measuring instrument called the anemometer. And that time was typically between 30 and 60 seconds. So we were using averaging times ranging between 30 and 60 seconds. If a structure is sensitive to 1 second gust, we cannot just design it for wind velocity averaged over 60 seconds and leave it there. That would be criminal. That would be not proper, not safe. So back in those days, we had to bring the average wind velocity up by applying a gust effect factor larger than 1. That's G sub B in the equation. Obviously, we can apply a gust effect factor to the velocity due to wind, or we can apply a gust effect factor to the pressure due to wind. Pressure being proportional to the square of the velocity, the two factors should not be the same. The factor that we apply to the pressure will be proportional to the square of the factor that we apply to velocity. Be that as it may, ASC 7 from the beginning has applied a gust effect factor to the pressure due to wind. So that's gust effect factor. As long as we used fastest mile wind speed as the basis of design, gust effect factor was always larger than 1. Today, we use 3-second gust speed as the basis of design. There are structures, short, stocky, big structures that are not sensitive even to 3-second gust, particularly shorter structures. So these days, most of the time, we bring the average wind velocity down by multiplying with a gust effect factor of 0.85. It is only some of the time that we will calculate a different gust effect factor and apply that to the 3-second gust speed. Okay? So this is gust. Accounts for the loading effects in the along wind direction, parallel to the direction of the wind due to wind turbulence structure interaction. The gust effect factor also accounts for along wind loading effects due to dynamic amplification for flexible structures. So flexible structures react more to wind than rigid structures, and that is taken into account through the gust effect factor. The factor does not account for other dynamic effects such as across wind loads. If you have a tall, skinny tower, when wind blows in the north-south direction, the predominant vibrations of the tower may be in the perpendicular east-west direction. And that kind of across wind phenomena will not be captured by the gust effect factor. Okay, so this is something I have been talking about, instantaneous velocity of wind as a function of time. As you see, the velocity changes from one instant to the next. Fastest mile wind speed, I explained to you the averaging time, the maximum wind speed averaged over 1 mile of wind passing through the anemometer. The averaging time was between 30 and 60 seconds. I think that's as much as we need to know. We switched to 3-second gust speed as the basis of design in ASC 795. It's 50-year return period, 3-second gust speed. This is something very important. This tells you that the shorter the averaging time, the higher the average wind speed. So 3-second gust speed would be larger than fastest mile wind speed. Okay, it is the same wind speed, but depending upon the averaging time, the number will be different. 3-second gust speed would be larger than fastest mile wind speed. 70 miles per hour fastest mile wind speed will be something like 90 miles per hour 3-second gust speed. I emphasize this is the same wind, nothing has changed. What has changed is the averaging time, and that changes the average. Okay. So on this picture, on the x-axis is averaging time, and on the y-axis is wind velocity averaged over t seconds divided by wind velocity averaged over an hour, which is 3,600 seconds. This tells you that 1-second gust speed is about 155% of hourly wind speed. So 1-second gust speed is about 155% of hourly wind speed. 1, 2, 3, 3-second gust speed is something like 150% of hourly average wind speed. Okay, 150% or so. So the shorter the averaging time, the higher the average wind speed. This is something you absolutely have to know and understand. So starting with ASC 795, when we switch to 3-second gust speed as the basis of design, the gust effect factor may be taken as 0.85 for all rigid buildings. G must be calculated for flexible buildings. G and the external pressure coefficient C sub P are lumped together and given to us in a lumped together manner in many situations in ASC 7 and Bnbc 2020. We will look at that as we go through the material. Okay, so sometimes it is G separate from C sub P, other times it is G and C sub P lumped together. Okay, so rigid buildings, flexible buildings. So far we have been talked about what those are. and that will change right now. So what is a rigid building? What is a flexible building? The definitions are all in section 213 of Bnbc 2020. A flexible building is a building that has a fundamental natural frequency less than 1 hertz. Scientists use frequency, engineers use period. Frequency is something I do not relate to. So I always have to translate to period. The frequency is the reciprocal of the period, okay? 1 over t. So when they say frequency less than 1 hertz, it means period more than 1 second. And we are talking about the elastic fundamental period, the first mode period. Okay. So a flexible building has a fundamental period larger than 1 second, and a rigid building has a fundamental period less than or equal to 1 second. So up to 1 second period, it is a rigid building. Beyond 1 second period is a flexible building. Now, very interestingly, having made a distinction between rigid and flexible on the basis of fundamental natural frequency or fundamental period, ACE 705 or BNBC 2020 does not tell you how to calculate that natural frequency or period. And that is a problem. Many people go to the earthquake provisions to calculate period, but that may not be the best thing to do. In earthquake design, the shorter the period, the more conservative you are. In wind design, the longer the period, the more conservative you are. So while AC7 did not give you anything up to the O2 edition except vaguely telling you that you can go to the seismic provisions to calculate your period, AC 705 included in the commentary, not in the standard, quite a bit of guidance. You can calculate the fundamental natural frequency in a number of ways. And those have been brought into AC 710. They were brought into the provisions. So I have given you quite a bit of material here, which looking at the watch, I will skip. So from this point on, where I say AC7 section 2692, I'm giving you material out of AC7, which will enable you to calculate the fundamental natural frequency or the fundamental period. I hope the material is self-explanatory. If not, I don't exactly know. There is only so much time and so much to cover, so I do not exactly know what to do. Anyway, this is the best that I could do. I am giving you material that you can use very directly in order to calculate the fundamental frequency of the fundamental period. Okay. Now, so we have talked about Q, the G. Now we have to go towards C sub P, the external pressure coefficient. Okay. This is again very, very basic stuff. Wind flow around building. So a building, because the building stands, as I keep on saying, it interferes with the free flow of wind. So the wind has to go around the building, around and over the building. Okay, it has no choice. And in the process of doing that, it applies pressure to the windward face of the building. It actually applies suction to negative pressure to the leeward face, the side faces, and also the roof of the building. So this is typically the pressure distribution. So this is the windward face, the roof, the windward roof, the leeward face, and there are obviously two side faces. On the windward face, we have positive pressure, meaning pressure above ambient. Ambient pressure is the pressure that would have existed if the building didn't exist. Pressure above ambient is called pressure. Pressure below ambient is called suction. So we have pressure on the windward face. We have suction on all the other faces, including the side faces. And you see very clearly that with a gable roof, the suction here is the highest of any point on the surface of the building. This is a a very basic problem in wind design. Because of that very high suction, the the windward roof may be sucked up. Okay, wind may suck it up, and when that happens, this wall loses lateral support, and then it doesn't take much for the wall to come down, and that's the end of the building. And that is a very typical failure mode in a windstorm. If you go after a hurricane to look, this is what has happened to many of the buildings. So the first challenge we have in wind design is to tie the roof down to the structure. There are hurricane straps and things to securely attach the roof to the structure. And once you have done that, the structure has to be attached to the foundation. This sounds very basic, but that I have seen buildings on the island of Kauai, in Hawaii, where after a hurricane, a building was several feet away from what it used to be before the hurricane, because there are no anchor bolts securing the building to the foundation. The building has flown. Okay, so the roof has to be secured to the building, and the building has to be secured to the foundation. Things that basic have to be paid attention to. Okay, so the external pressure due to wind is ambient pressure plus rho v squared by 2. The same term comes back. Okay, what we had in the expression for velocity pressure. Yeah, I should say that near the center of the windward face, there is a point called stagnation point where the positive pressure is the highest at any point on the surface of the building. And the pressure there is called the stagnation pressure. That's the highest pressure experienced anywhere on the surface of the building. And the stagnation pressure is equal to 1/2 rho v squared from physics. Okay, so pressure at any point is ambient pressure plus not at any point. The stagnation pressure is ambient pressure plus rho v squared by 2. And if we call pressure above ambient as the pressure P sub S prime, that is rho v squared by 2 at the stagnation point. Now, if we plot the pressures at various points on that, so I have taken a building and I've opened it up. This is the flat roof. This is the windward face. This is the leeward face. Those are the side faces. You see that at the stagnation point, and what is being plotted is pressure above ambient or pressure divided by the stagnation pressure, 1/2 rho v squared. So at the stagnation point, we have 1.00. But as we move away from the stagnation point, you see the numbers go down. However, over the entire windward face, the numbers are positive. But on the roof, the numbers are negative. On the leeward face, the numbers are negative. On the side faces, the numbers are negative, and so forth. Okay. So this is the actual pressure distribution. Now, complicated as this wind design is and sophisticated as it looks, we do not, in design, we do not consider this point-by-point variation. For the entire windward face, we take an external pressure coefficient of plus 0.8. For the side faces, we take an external pressure coefficient of negative 0.7, constant. For the leeward face, we take negative 0.5, negative 0.3, or negative 0.2, depending upon the L over B ratio, the plan dimension parallel to wind, no, anyway, dimensional ratio, it will come subsequently. So for the leeward face, it can be negative 0.5, negative 0.3, negative 0.2, depending upon the geometry of the building. So now we come back to the same basic equation, except that we know all the terms. P equal to Q, G, C sub P, everything has been explained. And I have told you that Q has to do with atmospheric effects, C sub P with aerodynamic effects, and G with both. Now, wind velocity increases with height above ground level. So wind pressure also increases with height above ground level. That fact is considered in design only on the windward face of the building. On the leeward face, we take a constant suction that is evaluated at the mean roof height level. The mean roof height is taken as the height to the point halfway between the eave and the ridge. Okay, so you go halfway from the eave to the ridge, and the height to the halfway point is the mean roof height. So on the windward face, we consider wind pressure varying with height. On the leeward face, it's a constant suction evaluated at the mean roof height level. On the windward as well as the leeward roof, it is also suction, typically constant suction evaluated at the mean roof height level. On the windward roof, we may have pressure, we may have suction, but we take constant pressure or constant suction depending, evaluated at the mean roof height level. And on the side faces also, we take constant suction evaluated at the mean roof height level. Okay, so complicated and sophisticated as our design looks, we have major simplifications built in. So variation of wind pressure with height is considered only on the windward face of the building. Okay. So far we talked about external pressure, but there is something called internal pressure that we may, in the design of a whole building, external pressure is what tends to be important. But if we are designing the wall of a building, we will have to deal with internal pressure, the pressure or suction inside a building. So this is a building or a tent or whatever. The point is that there is only a windward, there is an opening only on the windward face, or windward openings predominant. So in that case, more wind gets in than can get out, and we have positive internal pressure. In the second picture, there is only a suction opening, so more wind gets out than can get in, so we have negative internal pressure. And in the third picture, we also have a suction opening on one of the side faces, so more wind gets out that can get in, and so we have negative internal pressure. Okay. Now this this leads to very important enclosure classification. In AC7 and in Bnbc, we have three enclosure classifications: open, enclosed, partially enclosed. Okay, and please listen to me very closely. This is extremely important. So an open building is a building. This is the second item. An open building is a building that has at least 80% of each face physically open. 80% of each face physically open. That is easy to understand. There is no ambiguity about it, and I have never seen anybody confused about that. So that's an open building. Partially enclosed. A partially enclosed building has windward openings. It has suction openings, but the windward openings predominate. So more wind comes in than can get out. So internal pressure builds up. That is a partially enclosed building. Okay, one more time. A partially enclosed building has windward openings. It has suction openings, but windward openings predominate. So more wind comes in than can get out. So positive internal pressure builds up. That is a partially enclosed building. And then AC 7 says, if a building is neither open nor partially enclosed, it is enclosed. Okay, so let me start let me start again at a different place. A partially open building is a building that has windward openings, it has suction openings, but windward openings predominate so that more wind gets in than can get out. So we have positive internal pressure buildup. If a building is not partially enclosed by this definition, that building has to be either open or enclosed. Open means 80% of each face basically open. So if a building that is not partially enclosed does not have 80% of each face basically open, it is an enclosed building. By that definition, most buildings we define turn out to be enclosed. And the many parking structures that you are familiar with that have all kinds of openings, those are typically enclosed buildings. So enclosed does not mean enclosed in the dictionary sense. By going by the dictionary, you would expect a jailhouse without openings on the faces. Enclosed building of AC 7 is not that. It simply means it is neither open nor partially enclosed by the definition of AC 7 or Bnbc 2020. Okay. So when you bring the internal pressure into the picture, the basic equation P is equal to QG C sub P becomes what you see on the screen. Okay. Now you say P, the pressure on the build, or let us say pressure on a wall of a building, is the external pressure minus the internal pressure. Okay. The Q sub I is velocity pressure calculated for internal pressure. Most of the time, Q sub I can be taken equal to Q sub H. So I have two pictures that are very descriptive. Here we have internal positive pressure. So for this windward roof, external pressure is negative 1.2. It's a suction. The internal pressure is positive 0.6. So the net suction is the external pressure of negative 1.2 minus the internal pressure of positive 0.6, which is negative 1.8. Okay. So this is negative internal pressure. The next picture is positive internal. I'm sorry, the previous picture was positive internal pressure. This is negative internal pressure. Please take a look at the two pictures and you will get a full grasp of this G times C sub P minus G times C sub Pi, the external pressure minus the internal pressure. Okay, last thing before we go into details of Bnbc 2020, this is the last thing I will cover under the basics. So through ASC 7, Bnbc 2020, or any wind code you pick up around the world, there is a major pervasive division between the main wind force resisting system and components and cladding. Both are defined. Definitions are in 2.1.3 of Bnbc. But let me tell you a good way to look at it. Components and cladding receive wind directly. So they are loaded directly by the wind. Components and cladding are loaded directly by the wind. Main wind force resisting system derives its loading from components and cladding. It's not direct loading. Some of the time it may not be obvious whether something is directly loaded or indirectly loaded. Roof trusses many times fall in that category. The best advice in those cases is to treat the same thing both ways. You treat a roof truss as a component, you treat it as part of the main wind force resisting system. Whichever assumption produces the higher wind forces is the way to go in design. Okay. Now, for components and cladding, AC7 also gives us the pressure coefficients for design purposes. Those are area-based values. The pressure coefficient that AC7 gives us depends on what is called the effective area. Effective area is like tributary area, but it is not the same. Effective area is span length, time, and effective width that need not be less than 1/3 the span length. This is a very, very important definition. So effective area is the span length multiplied by an effective width that need not be taken any less than 1/3 of the span length. Okay? And the larger the effective area, the lower the pressure coefficient. Okay? Now, plus in the when you say plus something for a component in cladding pressure coefficient, it is into the component. Negative means out of the component. So pressure can be into the component or it can be suction out of the component. Okay, so this is the end of what I described as fundamentals or basics. Not that there are no more fundamentals to come, but anyway, from this point on, we will go into the provisions of Bnbc 2020, which are what do I want to say? Which are taken from AC 705. It's most of the time it's exactly the same, but there are some twists and quirks. One of which is that exposure categories B, C, and D of AC 7 is A, B, and C of Bnbc 2020. Okay, there are some little other things, but not a whole lot. Bnbc and AC 7 both specify a minimum design wind pressure, 10 pounds per square foot, which is half a kilonewton per square meter. This is for components and cladding. The component and cladding part is easy. Whatever you calculate cannot be any less than 10 pounds per square foot. For the main wind force resisting system, I want you to understand for all time to come that these are separate load cases. So, so the transverse direction of this building, we 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 will calculate the pressure distribution along the height of the wall and along the vertical projection of the windward roof. The idea is not that where the calculated pressure drops below 10 pounds per square foot, we make it equal to 10 pounds per square foot. No, we design for the calculated pressure distribution, and as a separate load case, we design for 10 pounds per square foot uniform acting on the wall as well as the vertical projection of the roof. Okay, so this is a separate load case. That's very, very important to emphasize and to understand. Okay, so after so much struggle, I see that here we left AC 705. That should be 2.1.3 terminology rather than AC 705. Anyway, so doesn't make any difference. So basic wind speed definition, this I already shared with you. 3-second gust. Now, no, actually I take it back. This is not a mistake. I was into anyway. Let me in view of the time, let me give you the short story. So in AC7, unlike in Bnbc 2020, the definition of V is 3-second gust speed 10 meters above ground of exposure C, which is in Bnbc exposure B. That part is identical. 3-second gust speed 10 meters above ground of exposure C, as long as you understand C is B of Bnbc. Now, the reason I left this slide in and left the AC7 title in is that in Bnbc, it is clearly said V corresponds to a 50-year return period. In AC 705, there is no reference to 50-year return period. That was removed. AC 702 had that. AC 705 says loads calculated from the wind speed map when multiplied by the wind load factor represent an ultimate load having approximately a 500-year return period. So that's what AC 705 defined as the basic wind speed, something that resulted in 500-year return period ultimate wind load. So you don't, this is a subtlety that you don't have to worry about. Stick with the Bnbc definition, and that definition is 50-year return period. So here, there is a difference between AC7 and Bnbc 2020, and the AC7 thing you can simply ignore. Okay, simple diaphragm building, a building in which both windward and leeward wind loads are transmitted through floor and roof diaphragms to the same vertical main. I don't know how much of it, how much it means when you read it. So I have later on a picture that I hope illustrates a simple diaphragm building. And that term becomes important because many things are for simple diaphragm buildings. Impact resistant glazing. Glazing which has been shown by testing in accordance with ASTM such and such or other approved test methods to withstand the impact of windborne missiles likely to be generated in windborne debris region, definition coming up during design winds. So impact resistant glazing. Then cyclone prone region. I went through that definition before. Areas vulnerable to cyclones. Bangladesh, these areas include the Sundarbans, uh, southern parts of Borishal and Patuakhali and Hatia, Bola, eastern parts of Chittagong, which I think should be western parts, and Cox's Bazar. Impact resistant covering. We talked about impact resistant glazing. This is covering. A covering designed to protect glazing, which has been shown by testing in accordance with ASTM, etc., etc. Mean roof height H, average of the roof eave height, and the height of the highest point on the roof surface, except that for a roof angle of less than or equal to 10 degrees, the mean roof height shall be the roof eave height. This is something important. So typically, mean roof height will be height to the point halfway between the eave and the ridge. So it will be A plus B divided by 2. But if the roof angle, this angle is less than 10 degrees, then the eave height becomes roof height. This is an important detail. Always keep that in mind, okay? Theta less than 10 degrees, which is a lot of roofs, actually most roofs. So the main roof height becomes the eave height. Openings, apertures or holes in the building envelope which allow air to flow through the building envelope and which are designed as open. This is important, which are designed as open during design winds as defined by these provisions. This is very important. What is an opening? And the answer is something that will remain open in the design wind event. So let us take a roll down door in a garage. Okay, it can be your parking garage, it can be a car repair garage. There is a roll down door. Whether the door is open or closed makes a huge difference. If you have a roll down door, you still have to design considering it as an opening unless you have a crew in place, instructions in place, making sure that the roll down door will in fact be closed at the approach of a storm. Okay, if you don't have those things in place, then you have to take that roll down door as an opening. So that's kind of important. Windborne debris region. These are areas within cyclone prone region. So within 1.6 kilometer of the coastal mean high water line, when the basic wind speed is equal to or greater than 150 meters per second, or in areas where the basic wind speed is greater than 54 meters per second. So not anywhere. So windborne debris region is part of cyclone prone region. That's the first thing. Within a cyclone prone region, if the wind velocity is more than 54 meters per second, you have windborne debris region. And within 1.6 kilometer, a mile of the coast, if the wind speed exceeds 50 rather than 54 meters per second, you have windborne debris region. Okay. So windborne debris region, we have major requirements that the glazing in the lower 60 feet of the building height be protected, and those will be coming up, you will see. So now comes some, I would call this is basic stuff. This is part of the requirements, but this is very basic. We have exposure categories that have come up from the beginning. Used to be A, B, C, D, now B, C, D in AC7, ABC in Bnbc 2020. What are they? What are the definitions? Exposure categories, there was a time exposure categories used to be directly defined. Not anymore. We now have definitions for roughness categories, and then the exposure categories are defined in terms of the roughness categories. Okay, so let us look at all of that. This is kind of complicated stuff, I will warn you. So for each wind region considered, the upwind exposure category shall be based on, well, let me not go into. So the idea is, so this is your building. You look at uh, 45-degree segments as shown in the picture. And so these would be upwind directions. Downwind will be away from the building, upwind. So for those two segments, you look at the roughness of the ground. And let me. So for each selected wind direction at which the wind loads are to be evaluated, the exposure of the building shall be determined for the two upwind sectors extending 45 degrees either side of the selected wind direction. The exposures in these two sectors shall be determined, and the exposure resulting in the highest wind loads shall be used to represent the wind from that direction. So if you are considering this direction of wind, you will look at the roughness in this segment, and whichever roughness gives you the higher wind speed is your roughness category. Surface roughness A definition is urban and suburban areas, wooded areas, other terrain with numerous closely spaced obstructions having the size of single-family dwellings or larger. Urban or suburban, wooded areas, other terrain, numerous closely spaced obstructions, and so forth. Surface roughness B, open terrain, scattered obstructions having heights generally less than 9.1 meters. That's about 30 feet. This category includes flat open country, as I mentioned to you already, grasslands, all water surfaces in hurricane-prone regions. I should have made it cyclone-prone. Anyway, so this category includes flat open country, grasslands, and all water surfaces in cyclone-prone regions. In cyclone-prone regions, when wind comes over the water, it is surface roughness B. Roughness C, flat, unobstructed areas, water surfaces outside cyclone-prone regions. So if you have a major lake or big river, wind comes over the river, it will be exposure surface roughness C. This category includes smooth mud flats and salt flats. Okay, so those were surface roughness categories A, B, and C. Now exposure A, B, and C. Exposure A shall apply where surface roughness A prevails in the upwind direction, always upwind, for at least 792 meters or 20 times the building height, whichever is greater. Okay, so I don't know that any explanation will make it any better. So exposure A shall apply where surface roughness A prevails in the upwind direction for at least 792 meters or 20 times the building height. There is an exception to that for buildings with mean roof height not exceeding 9.1 meters. The upwind distance may be reduced from 792 meters to 457 meters. Exposure B shall apply where exposure A and C do not apply. Okay, so this is defined by default. Exposure A is defined here, exposure C is defined here, shall apply where surface roughness C prevails in the upwind direction for at least 1,524 meters or 20 times the building height, whichever is greater. 1524 meters or 20 times the building height. Okay, that's exposure C. Exposure C shall extend into downwind areas of surface roughness A or B for a distance of 200 meters or 20 times the building height, which is greater. This is something important. So first we say exposure C shall apply where surface roughness C prevails in the upwind direction for at least 1524 meters or 20 times the building height. Then we say exposure C shall extend into downwind areas of surface roughness A or B for a distance of 200 meters or 20 times the building height, whichever is greater. Now, what downwind area is being referred to in the following sentence? Exposure C shall extend into downwind areas of surface roughness. Okay. We said that 2009 IBC made that sentence more easily understood. The 2009 IBC did not use the term downwind areas, did not make reference to surface roughness A or B, but simply reads exposure C shall extend inland from the shoreline for a distance of 200 meters or 20 times the height of the building, whichever is less. This is much, much better. So exposure C shall extend inland from the shoreline for a distance of 200 meters or 20 times the height of the building, whichever is greater. We have had questions over the years on this, so we tried to draw up a picture. So this is the shore. This is smooth water surface, that surface roughness C. Inland, it is surface roughness A or B. This is our building, and this height is Y. X has to be more than 1524 meters and more than 20 times the building height for this to be surface exposure, for this to be surface roughness C. Okay. Now, if you have exposure C here, the exposure C shall extend inland by a distance of 200 meters or 20 times the building height. So all of that will be exposure C. Actual exposure is A or B, but the exposure C shall extend inland by a distance of 200 meters or 20 times the building height. So that building, unfortunately, although it is away from the shore, will have to be designed for exposure C when wind comes into the building from the ocean. Yeah, and this time is running, but this 20 times the building height used to be 10 times the building height not too long ago. And I remember a call. It was from Saudi Arabia, someplace, and it was a huge desalination plant. And the engineers had designed it, and then the owner told them casually that the new edition of AC7 has come out. Why don't you, update your design to the new standard? And so when the building was designed, this Y distance was 200 meters or 10 times the building height. And the 10 times the building height distance meant that this building could be designed for exposure B and not C. But when that distance became 20 times the building height, the exposure became C rather than B. And designing for exposure C rather than B is a huge deal. It is pretty major. So 10 versus 20 doesn't look like much when you read, but these things have major practical connotations. Okay, why does exposure C extend so far inland, and why is it dependent on the height of the structure? This is a very important question. This exposure C extending inland is a significant issue. So answer is, after a change in surface roughness, wind has to travel sufficient distance over the new terrain for the velocity or pressure distribution to attain a new changed equilibrium state over a certain height above ground level. The required travel distance is a function of that height. Okay. You may have to read it more than once, but the explanation is pretty solid. Okay, for a site located in the transition zone between exposure categories, the category resulting in the largest wind forces shall be used. I think that should be understandable. In AC 705 commentary, there are some pictures that I decided to include for you. These are older pictures. I will not try to explain, but in your own time, take a look at the pictures and make sure that they go with what we provided by way of written material. Okay, wind design itself. We have three methods in Bnbc 2020. Method 1 is simplified procedure. Method 2, analytical procedure. Method 3, wind tunnel procedure. Okay. Under method 2, analytical procedure, there are two distinct and separate methods. The first one, that is the original wind design method going back to 1972. We loosely call it the all heights method. There is no height limit to the structures to which that applies. There is a second method that is a much more recent entry, that is a low-rise analytical procedure that came from testing sponsored by Metal Building Manufacturers Association done at the wind tunnel at the University of Western Ontario in London, Ontario. The name has very recently changed, but that's immaterial. The important thing is that under method 2, analytical procedure, there are two distinct and separate methods: the all heights method and the low rise analytical procedure. If you design the same building by the two procedures, you will not get the same answers. They are distinct and separate. Okay. Also, very importantly, the simplified procedure is a simplified version of the low-rise analytical procedure. Okay, that is kind of important. There is major resemblance between the two as a result. Okay, method 1, simplified procedure. From now on, I will skip more than I will cover because of obvious reasons. So most of this I will skip, but I have a couple of important things to say. So the simplified procedure, method 1, is restricted to, okay, let's read this. So this is, as I said, based on the low-rise analytical procedure. It applies loads on projected areas, not perpendicular to the inclined surface, but on projected areas. It is restricted to low-rise buildings having mean roof height less than 60 feet, also less than the minimum planned dimension, and it applies only to simple diaphragm buildings. Simple diaphragm building, the definition I showed you before, I told you that I'll give you an example. So let us look at this. So this is a concrete building. Wind is applied on the windward wall, whatever it is made of. This wall bending between supports provided by the slab at the top and the slab at the bottom will transfer the wind to the slabs acting as diaphragms. When we when we use the term slab, we are thinking of out-of-plane bending under gravity. When the same slab bends in its own plane under lateral loads, we call it a diaphragm. Okay, so this wall will transfer the wind applied to it to the diaphragms, as you see in the picture. Those diaphragms will develop tension along this edge. I'm sorry. This diaphragm will develop tension along that edge, compression along that edge, and shear along the parallel edges. The shear will be transferred to the supporting shear walls and frames, which will bring them down to the ground. Okay, so the applied wind is being transferred to the lateral force resisting systems, which are bringing them down to the ground through the floor and the roof diaphragms. Okay, so this is what makes it a simple diaphragm building. The wind is going through the diaphragms to come down to the ground. And concrete buildings are typically simple diaphragm buildings. There are a number of conditions for you to be able to use method 1, which I'm going to skip. So the method tells you that the pressure is equal to, and actually even this stuff I'm going to skip. This PS30 is given directly in tables. I will take you to the table. This is an importance factor that you are familiar with. K sub ZT you are familiar with. This is the topographic effect factor. The lambda, the P sub S30 is at 30 feet above ground of exposure, I believe, A. If you have a different exposure or a different height, then lambda is a conversion factor, adjustment factor. So PS30 is given directly in tables. That's what makes it a simple method, simplified design method. Okay, so this is what it looks like. The roof of the building, or the horizontal projection of the roof, is divided into areas E, F, G, H, and the wall and the vertical projection of the roof are divided into areas A, B, C, and D. This is for transverse direction of wind, this is for longitudinal direction of wind. For each of those areas, the PS30 value for A, B, C, and D for different wind velocities, the P sub S30 value is given in this table. Now, to my utter surprise, I found that this vital table was missing from Bnbc 2020. The copy I had, which I had every reason to understand was the very latest that was not modified, did not have this table. And I wrote this on the slide. Table is missing from Bnbc 2020. Then Pro Dasgupta of our office found that in the gazetted version, Bnbc 2020 actually refers to figure 6-2 of AC 705 for determining P sub S30, which is this table. This is table 6-2. Okay. So I think what happened is that this problem was discovered at the last moment. And instead of trying to insert a table, the easy way out was to tell the user, go to AC 705 table such and such. There are two problems with that. One is that you have to have the book. I don't believe that everybody in Bangladesh has that. Secondly, you have to understand that where AC7 talks about exposure B, it is exposure A of Bnbc 2020. Okay, until and unless you catch on to that, it will be difficult to use this table. So these values are for exposure A, mean roof height of 30 feet, K sub ZT of 1, and I of 1. So you have to apply a topographic effect factor as you saw on the equation. And if you have anything other than exposure B and mean roof height other than 30 feet, then you go to this conversion factor table, the lambda. Lambda give you for different exposures and different mean roof heights, an adjustment factor as it was called. So PS30 will come out of the table that is missing in Bnbc 2020. Importance factor you are familiar with, K sub ZT you are familiar with. P sub S30 is for exposure A, 30 feet of mean roof height. If you have any other exposure, other mean roof height, this is the adjustment factor that is given by the table that I just showed you. Okay. So this is method 1. No matter what I do, I don't think will be done by 11:15 today, not 11, whatever. The 10:15 here, 9:15 your time. Now, what I just showed you for method 1 was the main wind force resisting system. I did not even go to components and cladding. Okay, I want to mention that. I didn't even put that into the slides. Method 2, analytical procedure. Again, I'll stay with the main wind force resisting system, at least mostly. Rigid buildings of all heights. So these are not flexible buildings. Gast effect factor is G, typically 0.85. For flexible buildings, Gast effect factor is denoted as G sub F. This is just a matter of notation. We have seen this equation already. P, pressure due to wind, is external pressure minus internal pressure. Okay. External is Q G C sub P, internal is Q sub I G C sub Pi. The Q sub Z expression we have seen already. The constant V squared, K sub Z, K sub ZT, K sub D, and I. The Q sub I, the velocity pressure for internal pressure, that is being described here. Most of the time you can take it as Q sub H, but I will let you read it instead of trying to spend time on that. Directionality factor K sub D, I have described for you. And yesterday I mentioned to you, some of you might remember, the normal load factor on wind in strength design is 1.6. But if your wind does not include directionality because it came from wind tunnel testing rather than from AC7, then the load factor of 1.6 will go down to 1.3. So there is a direct correlation between the directionality factor and the load factor on wind that we use in strength design. Okay. Now the method 2 in steps. First is find wind speed V and the wind directionality factor K sub D. Okay. Second is find importance factor I. 3, for each wind direction, establish your exposure category. And once you have your exposure category, you can calculate the combined height and exposure coefficient K sub Z and K sub H. So let us look at where those things come from. The wind velocity V will come from this map. In addition to the map, you have, I think you should be very thankful in Bangladesh Building Code for most significant communities in the country, you have the design wind pressure listed in a table. So for Dhaka, it is 65.7 meters per second. Nothing could be any easier than that. You don't have to do any interpolation, anything. So this map tells you that you use tabulated values. If you don't have tabulated values, if you're in one of those zones, you use the value for the zone. If you are outside of the zones, then you interpolate between contours, unless you sit on a contour, in which case the value of the contour is your wind speed value. Okay? So V is made very easy to figure out, the wind velocity. K sub D comes from this table, that is 6 to 12 of Bnbc 2020. And K sub D, very importantly, is 0.85 for all buildings, component and cladding, as well as main wind force resisting system. Importance factor comes from this table, 6.2.9. Okay, so cyclone prone region, you have a set of values. Well, actually, the so importance factor, as I said, is 1.15 for important buildings. That would be occupancy category 3, where a lot of people congregate in one space at one time, or occupancy category 4, essential facilities and hazardous facilities. 2 is standard occupancy building, 1.00, and for the unimportant building, it is 8.7 in inland areas and 7.7 in cyclone prone regions, and those are defined. It's wind velocity more than 44 meters per second. This is wind velocity between 38 and 44 meters per second. The exposure category, how you establish whether you have A, B, or C, we have gone over. Once you have your exposure category, you can calculate K sub H, not calculate, you can determine K sub H, which is the K at the mean roof height level, or K sub Z, which is at any height Z above ground level from this table. Okay. Now, so this is exposure A, this is B, this is C. Case 1 and case 2, one is for main wind force resisting system, one is for components and cladding. For exposure B and C, there is no difference between main wind force and component and cladding. But for exposure category A, there is a difference between main wind force resisting system and components and cladding, only up to height of 15.2 meters. After that, the numbers are all the same. Okay. So this is K sub H, K sub Z. The table goes up to 500 feet, 152.4 meters. If you have a taller building, you find your K sub Z and K sub H from these expressions. Okay. And to use these expressions, you will need Z sub G, the gradient height, and the alpha, which we talked about already. Z sub G, remember, are those values for exposure categories A, B, and C. For C, it is 213 meters. And the alpha values are those for exposure categories A, B, and C, 7, 9.5, and 11.5. So we are by no means restricted to 500 feet of height. We can calculate K sub Z, K sub H at any height we like using those expressions. So beyond that, we have to determine topographic effect factor K sub ZT, gust effect factor, enclosure classification, open, partially enclosed or enclosed, internal pressure coefficient, and then external pressure coefficient. So it's quite a bit. The K sub zt is a complicated coefficient. Depends on three factors, K sub 1, K sub 2, K sub 3. Those are given in this part of figure 6.2.4. I have no way of going into the details or any intention. All I'm trying to do is to point out that everything is in Bnbc. So figure 6.2.4 will give you your K sub zt if you have a building located on the upper half of a hill ridge or escarpment. If you have the typical Dhaka building on plain land, K sub z is equal to 1. You don't have to worry about all of this. G, as I kept on saying, is 0.85 for rigid buildings, period, less than or equal to 1 second. You can take 0.85, or if you like, I do not know why you would like that, you can calculate the gust effect factor, and in that case you need 1, 2, 3, 4 equations and a table. If, however, you have a flexible building, period exceeding 1 second, you have no choice but to calculate gust effect factor. Now there are something like 13 equations involved. The equations get uglier as they go. And once a long time ago, I decided to calculate G by hand to find out how much pain it was. And it took me, believe it or not, an hour and a half of hard work. And the G that I found was 0.86, which was almost a joke. So rigid building, it is 0.85. After spending hour and a half, I had calculated 0.86. I have since found that much of the time, if you calculate G as you are required to, it comes out between 0.85 and 1. I do not know enough about the subject to tell you why. I'm not saying that you never calculate more than 1, you do. But AC7 also tells you if your G is very large, definitely exceeding 2 in the range of 3 or 4, you should not apply the all heights method. Then you need to do sophisticated dynamic analysis, which no one knows how to do, or you have to go to wind tunnel testing. Okay, so anyway, the calculation of gust effect factor for flexible buildings is a project in itself, unless you have spreadsheets and so forth set up in your design office. Open building, partially enclosed building, and enclosed building. I gave you the definitions in principle. These are definitions in specific terms, in terms of how much windward opening, how much suction opening. I will let you read this. These are according to what I described to you. An open building is typically not a building. It will look something like this. 80% of each face physically open. So partially enclosed building, remember, there are windward openings, there are suction openings, windward openings predominate. The mathematical expressions for that are here. And enclosed building is a building that does not comply with the requirements for open and partially enclosed buildings. By the definition of AC7, this parking structure is an enclosed building. Okay, I absolutely want you to appreciate that. Okay, this is an enclosed, typical enclosed building of AC7. It is neither partially enclosed nor open. Windborne debris region. Glazing in buildings located in windborne debris region shall be protected with an impact-resistant covering or be impact-resistant glazing according to the requirements specified in 18, etc., etc. So the way it is for the first 30 feet of a building's height, 30 feet is 9.1 meters or something. The building, the glazing or the covering has to be able to withstand the impact of large missiles. Those are typically 2x4 starts thrown at a certain speed on the glazing or the covering. From 30 feet from ground to 60 feet from ground, the glazing has to be able to withstand the impact of small missiles. Okay, so those are the two tests. One is a large missile test, one is a small missile test. So glazing in a building located in windborne debris region shall be protected with an impact-resistant covering or be impact-resistant glazing. Now, glazing in category 2, 3, and 4 buildings. 1 is the unimportant building. Remember, 2 is standard occupancy, 3 is assembly, 4 is essential facility. Located over 18.3 meters above the ground, that's 60 feet, or over 9.2 meters above aggregate surface roofs located within 458 meters of the building. So it is 60 feet above ground or 30 feet above the aggregate surface roof located within about half a kilometer of the building shall be permitted to be unprotected. Okay, above a certain height, beyond 60 feet, you can have unprotected glazing. And category 1 buildings, the unimportant buildings, you don't have to have protective glazing. Internal pressure coefficients G times C sub Pi. Open buildings, wind simply flows through. There is no internal pressure buildup. G times C sub Pi is 0. Partially enclosed building, remember, pressure builds up. Wind gets in, cannot get out. Now, those buildings we design for an internal pressure coefficient of plus minus 0.55. Enclosed buildings are between open buildings and partially enclosed buildings. G times C sub Pi is plus or minus 0.18. Internal pressure we always consider both ways because for some walls the positive is more critical, for some other walls the negative is more critical. For partially enclosed buildings containing a single unpartitioned large volume, the internal pressure coefficient G times C sub Pi can be reduced. And there is an expression which I will not spend time on. C sub P, very, very important. And I will keep to the basic cases. Okay, so this is a gable roof building. The other buildings have different roofs. That's all. Okay, so sorry, time becomes a problem. I get a little flustered. Okay, so this is the windward face of the building. This is the leeward face. This is the leeward roof. This is the windward roof. These are the side faces, and we need C sub P for all the faces. For the walls, the coefficient come from this table or figures. This is one problem in ASC 7 carried over into Bnbc. You don't know what they call a figure and what they call a table. And after a long time, I figured out for myself that when something starts with a figure, no matter how many tables follow, they call it a figure. And if you start with a table, no matter how many figures follow the table, you call it a table. And that causes a lot of confusion. And the tables are placed after the figures. Anyway, for the windward wall, C sub P is plus 0.8. I told you a long time ago. We do not consider point by point variation of wind pressure. And the 0.8 is applied with Q sub Z, wind pressure varying with height. For the leeward wall, depending upon the ratio of L over B, L is plan dimension parallel to the wind, B is plan dimension perpendicular to the wind. Plan dimension between 0 and 1, it is negative 0.5. plan dimension ratio of 2, negative 0.3, plan dimension ratio of 4 or more, negative 0.2. Between 2 and 4, you will interpolate between negative 3 and negative 2. Side walls for all values, it is negative 0.7. So the walls, the external pressure coefficients you get from this one table. For the roof, it is a little more complicated. Roof pressure or suction comes from this table. This is the pitch of the roof, the angle of the roof. This is the windward roof. This is the leeward roof. Wind normal to the ridge for the steeper roofs, theta larger than or equal to 10 degrees. This is wind normal to the ridge for flatter roofs and parallel to the ridge for all roofs. Okay, so this is wind normal to the ridge for the steeper roofs. This is wind normal to the ridge for the flatter roofs, and wind parallel to the ridge for all roof angles. Okay, the pitch of the roof is here, and the height, mean roof height to plan dimension parallel to the wind is this parameter. Okay, so the C sub P will depend upon the angle on the roof of the roof and the mean roof height to plan dimension ratio, plan dimension parallel to the wind. Okay, that's pretty much as far as I can take you. This table to digest will take you a little time, but the important thing is that C sub P is given for the not only the walls but the roof of the building. So everything you need for the design of a building is given to you in the standard, in your case in Bnbc 2020. These copious notes go with the roof C sub P table, and almost everything said, not everything, but half the things said in the notes are deadly important. Then there is this low-rise analytical procedure. There are 3 slides that I have included, which I knew when I included them, I had no way of covering, but it is in there. Okay, so the low-rise analytical procedure. The Q sub Z, Q sub H, you know where to get them. And the final 2 pages, which I probably will not try to go too deep into, puts it all together. So a rigid building, irrespective of height. Okay, pressure, this you have seen before. P, pressure on the building, is Q, G, C sub P, we know every term, minus the internal pressure Q sub I, G times C sub Pi. G times C sub Pi we now know is plus minus 0.18 for enclosed buildings, which are most buildings, or plus minus 0.55 for partially enclosed buildings. Q sub I most of the time can be taken as Q sub H. That would be a conservative thing to do. Okay, C sub P we just looked at. G we have talked about, mostly 0.85. Q, the velocity pressure, that is the 00613 V squared. Q sub Z, Q sub the topographic effect factor, Q sub ZT times, not Q, I mean K sub ZT times K sub D times the importance factor. So all of that is Q, and we know where to get all the components. Okay, so this is for a building of any height. When it is a low-rise building, even on the windward face, we do not use Q sub Z. It is Q sub H for all faces of a low-rise building. And The external pressure coefficient is a lump together G times C sub PF, and the internal part is same as before, G times C sub PI. So between here and here, the difference is both Q for the windward face and Q for all external pressure, including external pressure on the windward face, is now Q sub H. And the Q sub I is also Q sub H. And external pressure term, there is no separate G and C sub P. It is G times C sub PF. Okay. So on and so forth. You have, if you have a flexible rather than a rigid building, what changes is G becomes G sub F. Otherwise, there is no difference between this and that. Okay. So I will kind of leave it there. There are 2 pages of these covering all these situations that are addressed in Bnbc 2020. Okay, the final method 3, wind tunnel testing. I will tell you only a couple of things and be done with that. That will leave us at least a few minutes for a few questions. Wind tunnel testing is always allowed to be done. That's the first thing. You want to do it for a 3-story building, you want to design it based on wind tunnel testing, you are welcome to. It will be an expensive proposition, but so be it. Most of the time, any building in Chicago exceeding maybe 20 stories, which isn't much, is designed based on wind tunnel testing. Simply because you get to design the building for lower pressure than you will calculate out of ASC 7. It is a fact. Okay. And in one of the slides, we tell you why that is so. Why wind tunnel test pressures come out to be lower than the ASC 7 pressures. But that is a huge motivation for doing wind tunnel testing. And because the pressures come out to be lower, this is not a requirement, but in the commentary, ASC 7 tells you do not go below 80% of what ASC 7 would have given you. That is for the main wind force resisting system. And that is also for zone 4 of the walls and zone 1 of the roofs for component and cladding pressure. That detail we need not go into. All I'm saying is that the commentary tells you do not go below 80% of what ASC 7 would have given you. And that is not mandatory. And everything I'm telling you, almost everything has changed. This is ASC 705. Here it is ancient. We are almost done with ASC 722. ASC 705 was replaced by ASC 710. That was replaced by ASC 716. We have almost completed ASC 722, which will be used starting in 2024. Okay, so this is, much of this is old, but anyway, I do not want to go to newer standards. Only once I did, to give you the calculation of fundamental frequency or fundamental period, because that I thought was the best source that I could give you. Okay, for cladding design, the wind tunnel testing turns out to be very, very important. You can get a very detailed idea of what you are dealing with. It is not the cladding, the attachment of the cladding to the building that is typically the problem. There is a lot of stuff here. Pedestrian comfort is a it is, so you have a tall building, and that, particularly in downtown areas where there are many tall buildings, the airflow around the buildings depends on the design of the buildings, how tall they are, and so forth. And there are literally places when you walk by the side of a building, it is difficult to keep your clothes on. The wind is so high. And these things can be figured out beforehand in wind tunnel testing. You the pedestrian comfort is a consideration that you cannot okay. Anyway, let me show you 3 or 4 pictures. These are all pictures, but very revealing pictures. This is Professor Jack Cermak himself. To start with, we had a wind tunnel uh, at the University of Western Ontario, London, and the second one was at Fort Collins, Colorado, Colorado State University. That's where Cermak was, and he started it. In London was Alan Davenport. Now there is a major one in Guelph, Ontario, that's totally private. Anyway, so this is typical wind tunnel testing. You simulate the roughness of the ground here by putting different kinds of carpets and things. These are models of the buildings, not only the building that you're designing, but also neighboring buildings, because the neighboring buildings will have an effect on your building. The model of your building will be heavily instrumented. The neighboring buildings will typically not be instrumented, but the important thing is that everything be to scale. That is vitally important. And when you have modeled the neighborhood, you can play what if scenarios. What if a neighboring building were to disappear? What if a tall building, what if this short building would one day be replaced by a tall building? You can play those scenarios in the wind tunnel. This is a Chicago building that was tested out. This is near the lake shore. Again, the same story. The building that is being designed in the wind tunnel is heavily instrumented. The neighboring buildings not instrumented but modeled to scale. This is a power station on the edge of a major gorge or precipice or whatever. There is no way to design this except through wind tunnel testing. So they have put the whole thing in the wind tunnel. The power plant, obviously a scaled down model of it, the terrain and the surface over which wind is expected to come. This is the in front of the Louvre in Paris, the IMP designed this pyramid that somehow complements the old building. Anyway, the pyramid had to be tested in the wind tunnel. This is obviously important. This is in the middle of Paris. This is close to the one of the most famous museums or art galleries in the world. So everything had to be carefully done. And this is the wind tunnel testing of that pyramid. Okay, so this is the sketchiest idea of wind tunnel testing. Now there is an ASTM not ASTM, ASCE standard on wind tunnel testing. I forgot the number, 59 or something. Anyway, that's probably not important. So method 1, simplified method. Method 2, analytical procedure. Method 3, wind tunnel testing. Method 2 has the all heights method and the low rise analytical procedure. Hopefully, I have been able to give you an idea at least of this vast topic. At least the basics, I hope, were reasonably well covered. And I have only 7 minutes or so for questions. So let us see what happens. Okay, first one says, should internal pressure coefficient be considered for multi-story flat roof RCC building? Should internal pressure coefficient be considered for multi-story flat roof steel building? Should internal pressure coefficient be considered for multi-story steel building with top roof pitched? Whether you consider internal pressure does not depend on whether it's a concrete building or steel building or what kind of roof. It depends on what you are doing. If you are designing the wall, let us say the exterior wall of a building, the outside is subject to external pressure. The inside of the wall is subject to internal pressure, which can be positive, which can be negative. So this wall has to be designed for the external pressure minus the internal pressure, or the external pressure plus the internal pressure. I gave you two pictures in the slide set. Please take a look at them. So depending upon what you are designing, you may have to consider internal pressure irrespective of the type of your building or the type of your roof. If you are designing the entire building, okay, then internal pressure does not come into play. It cancels out. So that's what it is. Second, should internal pressure coefficient be considered for multi-story flat roof? Seems to be the same question. Yeah. Okay, this one. Wind load for flat roof building is not clearly specified in Bnbc 2020. I don't know that that is true. It's theta equal to 0. So when something is for theta less than or equal to 10 degrees, that includes flat roof. In method 2, wind load for low rise says for flat roof, slope will be 0 degree. My question is that according to this method, do I have to assign roof loads? Do I have to assign roof loads zone 2E, 3E, 2, 3 in flat roofs? If yes, can you tell me the procedure for assigning roof loads in? Yeah, this is spelled out. I don't remember off the top of my head, but flat roof is so the basic thing is that half of a flat roof is considered to be the windward roof, the other half is considered to be the leeward roof. It is not that flat roof is not provided for. And I think if you keep that in mind, I think your problems will be solved. So try this, and if that doesn't work, but it is in there. I know for sure that it is all spelled out. But the main thing you want to know is a flat roof, as I said, is a roof with an angle of 0 degree. And when you have a flat roof, there is no ridge. So you imagine a ridge halfway down the roof. So the front half will be the windward roof and the back half will be the leeward roof. And that hopefully will solve your problem. Okay. In some load combinations, the roof live load L sub R is not considered. So while designing any structure, are we allowed to exclude roof live load L sub R in some specific combinations? Can you please explain this and some? Okay, it's not a question of example or explanation. So there is floor live load, there is roof live load. On the roof, you will consider roof live load. On the floor, you will consider floor live load. So when you are designing a floor, the roof live load doesn't come into the picture. And when you are designing the roof, the floor live load does not come into the picture. Unless you have a special purpose roof or something, then it is like a floor. So when you are designing a roof, go for the load combinations that has the roof live load. When you are designing a floor, go for the load combinations that have the floor live load L. It is really as simple as that.
I believe
Which
the
type?
question is regarding if you're designing a column or a shear wall, and you're calculating the axial load, a load on a column, so let's say. So it will support both the roof and the floor.
Say that one more time.
When you're designing a column, let's say, or a shear wall, and you're trying to, let's say, calculate the axial load on it, so then there it will get loading from both the roof and the floors above it.
Yeah.
So the question is regarding that. Like, do you so when you consider different load combinations for that column at the, let's say, first floor level?
But I don't see any problem. You use the load combinations including L sub R, you use the load combinations excluding L sub R, whichever gives you the higher is your load.
No, there is no problem. The question, the person is asking is that if that is correct, that we are allowed to exclude roof life load L sub R in some specific combination.
That is true.
And the answer is yes.
Yes.
In some combinations where the roof life load is not included, you're allowed to exclude, yes.
Yes. Okay. Which time period should be used to calculate gust effect factor for flexible building? Software calculated time period or by the formula given in the code. So if you please read what I reproduced from ASC 710, you are always allowed to calculate the fundamental frequency or period, as you say, software calculated, that is always allowed. Now, instead of doing that, you may want to use the approximate fundamental frequencies that are given in ASC 710. It is really your choice. Okay, so in seismic design, we have limitations on rationally computed period, as we call them. In wind design, I am not aware of those limitations. So make sure that when you do your period or frequency calculation, that the stiffness assumptions make sense, that you are not trying to do something strange. Here. Directional procedure does not cover in this presentation. Directional procedure term was not used in ASC 705. That is a later term. Okay? But now that you bring it up, so we have method 1, method 2, and method 3. Under method 2, analytical procedure, I kept on saying that is the all heights method and the low rise analytical. The all heights method, which is part of method 2, in that method, the wind direction counts. The wind pressure that you calculate depends upon the direction of wind. That is the directional procedure. In the low rise analytical procedure, the wind direction does not count. Components have been, or buildings have been tested in the wind tunnel under all conceivable wind directions, and the envelope values are given. So the low rise analytical procedure as well as its simplification, which is method 1, are called envelope procedures, starting with ASC 7. 10 is when the reorganization was done. Yeah. So the all heights method is now directional procedure, and the low rise analytical and the simplified are now envelope procedures. Okay. In case of multi-gable steel shed building, what will be L and B? The shape of the roof has nothing to do with L and B. L is the plan dimension of the building parallel to wind. B is plan dimension of the building perpendicular to wind. unless I'm missing something in the question, that is the answer. What does it stand for 3-second gust speed at 10 meters above? Why this time and height is restricted? It's not restricted. It is part of the definition. What is the definition of 3-second gust speed? No. What is the definition of basic wind speed V that is mapped in Bnbc 2020? That's what this is about. What is this V basic wind speed that is given in map that we use in wind design? It is 3-second gust speed at 10 meters above ground of exposure B, corresponding to a 50-year return period. So there are 4 elements to the definition of V. You have to understand all 4 elements to be able to do wind design. This is very, very basic. These are not restrictions. These are not restrictions at all. This is definition of basic wind speed. It's again 3-second gust speed. That means wind averaged over a period of 3 seconds at 10 meters above ground of exposure B, corresponding to a return period of 50 years. Okay, I think I will have to quit. We have another meeting in 15-20 minutes. Let me try the next one. It's a long one. Let me read. According to AC 705, section 26.2. Section 26 of AC 705. There was no section 26. I'm confused. Are you talking about AC 710 maybe? I don't know. Low-rise building is enclosed or partially enclosed building which mean roof height is less than or equal to 60 feet. And you said that these buildings are permitted to be considered as rigid. I do not know at this stage what is being said. Low-rise building, this is within quote. Low-rise building is enclosed or partially enclosed building which mean roof height is less than or equal to 60 feet. And you said that these buildings are permitted to be considered as rigid. But if the mean roof height is 70 feet or 80 feet, then according to code or after calculating natural frequency, if we get less than 1 hertz, this type of building are classified as flexible building, right? However, in the context of Bangladesh, the roof height usually 10 feet. So we can treat a 6-story. I do not know. The question apparently continues. It's not very clear to me. I'm sure there are many, many more questions. And as I said yesterday, I do not quite know how to deal with these questions, except we are trying to find a way. But when something is of this kind where we do not understand, I do not know exactly what the choice is. Anyway, at some point we'll try to read and understand and hopefully be able to answer. And that maybe towards the end of the series, when the structural part is done and we don't have to instruct anymore, other people are instructing, maybe we can get to the questions. Okay, thank you very much. There is no way to answer a large number of questions in 2.5 hours. And more than that goes late into your night. So we are doing the best we can. So hopefully you got something out of the presentation. Thank you so much. Next week, we'll talk about earthquakes, and that will be more fun. Thank you. Bye.